All right, section 9.4, permutations and combinations. You may or may not have seen this notation before. It's called a factorial. So a factorial actually means, so we're going to take n factorial as our example, means we take n and we multiply it by 1 less than n, that's n minus 1, and 1 less than that. And we keep going and multiplying this all the way down to 3 times 2 times 1. And then we need a definition for what happens when we have 0 factorial. And I know it feels sort of funny to say that 0 factorial is anything other than just 0, but you'll see why it needs to be this way in a little bit. It is defined as the value 1. So if you see 0 factorial, it actually means 1. Obviously, it doesn't fit in with that description at the top at all, because that only makes sense if I'm dealing with numbers that are bigger than 1, right? Okay, or at least as big as 1. All right, so we're going to do an example. Our example is 4 factorial. Do you guys want me to turn one more light on, or is this good? We're good? Okay, you're not going to go to sleep on me, are you? Okay. All right, so 4 factorial. What would I actually be multiplying if I were doing 4 factorial? Start with 4, right? And then what? What was that?
Yeah, 3. I said 4 minus 1.
Yeah, 4 minus 1, so 3, and then 2, and then 1. All right, so somebody grab a calculator or do it in your head or whatever. 4 times 3 times 2 times 1. Yeah, it's 24. All right, so some of the numbers that we're going to be doing factorials with are going to be small, like this one. Maybe you can do it in your head. Others are going to get quite large, and you're not going to want to do them in your head. So if you want to grab a calculator right quick, you're definitely going to want it later on. So for those of you who've had number theory actually covers chapter 2 in your textbook. And this is coming from chapter 2. It's talking about the fundamental principle of counting. So the fundamental principle of counting says the following. If event m can occur in little m ways, and event n can occur in little n ways, then capital M followed by little n, followed by capital N can occur in mn ways. So it's talking about ways of getting certain things to happen. And as an example of that, we're going to talk about Pizza Planet, which is in what movie? Toy Story, that's right. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meal deals consist of 1 salad, 1 pizza, and 1 dessert? So what the fundamental principle of counting says is that I would multiply. I'm going to leave spaces as like placeholders, like this. So my 6-year-old's learning how to fill in the blank, and it's really confusing to her when I read like a scripture and I say the word blank in there, and she repeats the word back to me, blank, and I'm like, no, you got to fill in the blank, right? We're filling in the blank with numbers. These are our 3 blanks. The first blank represents, what did it list first? Salad. How many different salad options do I have? I have 3 to choose from. The second blank represents pizza. So how many pizza options do I have to choose from? 15. And then the last blank represents desserts. And how many desserts do I have to choose from? 4. Okay, so this isn't a factorial. This is just different ways of counting when I'm organizing things. One of the questions that I do in number theory, I think, is outfits. Like how many outfits can you create when you have this many shirts, this many pairs of shorts or skirts or whatever it was, and this many pairs of shoes? How many different combinations of those things can you have? So there's lots of things that we can organize and structure in this way. What is 3 times 15 times 4? 180, and this would be different meals. I'm still on my screen in this classroom, that's good. I go off the screen when I enlarge my screen like this in my other classroom. 180 meals. Okay, there are, I think it's 3 different types, well, there's 4. There's 4 different types of counting methods that we're going to learn. This is one of them, fundamental principle of counting. We're just counting the number of items that happen in succession. Like it happens this many ways here, and then this many ways, and then that many ways, right? So this is one of our 4 methods. Method number 2 has to do with permutation of like objects. So n elements, we're going to choose R1 of them which are alike, R2 of them are alike, and alike objects are indistinguishable. So if I have a permutation of like objects, I'm going to give you an example in just a second. The way we calculate it is we do n factorial on top, and then all my different individually indistinguishable objects and how many of them there are with factorials go in the bottom. And our example is going to be with candy. I wish I had candy. That would be nice. I should bring you guys candy sometime. Starburst. So you guys have seen the Starburst containers, right? I don't know exactly how many there are. This is a made-up problem, but we're going to pretend that it's real. There are 4 colors in a traditional Starburst roll. There's yellow, red, pink, and orange. So this is an example where there are 4 red, 5 pink, 3 yellow, and 2 orange. Okay? Now, it's indistinguishable whether I pick orange number 1 or orange number 2, right? They're the same thing. They're different, right? They're 2 different pieces of candy, but they're the same thing. So that's what this is talking about when it talks about something that's indistinguishable. I think there's one in your book that talks about running flags up a flagpole, and you have like 3 red flags. Well, it doesn't matter which red flag you put up, right? They're the same thing, but they're different objects. They're indistinguishable. So that's what that phrase is meaning. So the question is, how many different ways can you eat the Starburst? In terms of flavors, right? In terms of flavors. Well, those indistinguishable objects don't change anything. It doesn't matter if I eat orange 1 before orange 2 or orange 2 before orange 1. They still taste like orange, okay? So the way that I do this is I first would count up how many Starburst I have. So how many are there in this scenario? 14. So that's my number that goes on top, the total number of objects, 14. And then my denominator is the individual number of indistinguishable objects. For example, how many reds do I have? 4. So there's a 4 factorial down here. How many pinks do I have? 5. Have you guys seen the Starburst packages that are all pinks? That's my kind right there. How many oranges are there? Or how many yellows? Yellows are listed next. 3. And then how many orange? 2. Okay, now this isn't a very good example of what I'm about to tell you, but there are some where the numbers get too large that you can't just like plug them in your calculator. Like you can't, here's 14 is probably still small enough that you could tell your calculator 14 times 13 times 12 all the way down to 1 and it would give you a number. But eventually when you do that with big enough numbers, the numbers are so large that your calculator turns things into scientific notation and it won't write them all out because your screen's not long enough. Does that make sense? So in general, what we want to do is we want to find a way to use your calculator effectively with the numbers not getting too large to be able to be done. So what we are going to do is we're going to write down 14 until it matches with one of them on bottom, and the biggest one on bottom is 5. Everybody with me? So I'm going to write down 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 factorial. Okay, because I could write 5, 4, 3, 2, 1, but that's the same as 5 factorial, so I'm going to stop short of writing them all out. I'm going to leave my 5 factorial. And then in the denominator, you see that I have a 5 factorial. I'm just going to list it first. Now, all the rest of them in the denominator, I'm going to write them out. So I'm going to have 4 times 3 times 2 times 1. I've got a 3, so I have a 3 times 2 times 1. And I've got a 2, so I've got a 2 times 1. So everything's written out except for the largest one that matches on top and bottom. Now, if they actually match in entirety, I don't mean like, oh, they both have a 2 in common. That's not what I'm talking about. They actually completely match, right? Just like this 5 factorial completely matches this 5 factorial. If they absolutely completely match, they will cancel one another out. Because what they represent is 5 times 4 times 3 times 2 times 1, which is exactly the same on top as it is on bottom. We just didn't write it out. So these two will cancel. Everything else will also cancel from the denominator into the numerator. They have to. Because I can't have a fractional number of ways that something can happen. It doesn't make sense, right? This answer has to be a whole number, which means every piece of that denominator must cancel with something on top. Now, you can cancel it in lots of ways. I tend to look for numbers that actually match the things that are on top. Like, look, here's 4 times 3, and there's a 12. That's nice. All right, I got a 2 for 1. Here's a 3 times 2. There's a 6. It doesn't always work that way because, as you can see now, I have a couple of 2's left, but 2 times 2 is 4, and there's not a 4 on top. But 2 times 2 is 4, and there's an 8 on top, and 8 divided by 4 would be 2. So they'll cancel, they just may not cancel out completely when I'm factoring out the little bitty individual pieces. Now, everything in the denominator is now just ones. You need to be a little bit careful when you're looking back at your numerator that you sort of capture everything and you don't miss any of them, right? I need a 14, a 13, an 11, a 10, a 9, a 2, and the 7 could, it could feasibly get disappeared, right? Because it's sandwiched in the middle of things. So be very careful that you don't lose any of your values. Everything that I circle in blue now needs to be multiplied together, and it will give you a large value when you're done, by the way. So what is it when I multiply those values out?
1,261,000.
I think you missed a 2. Yep. That's what I had. Yeah, it's 2,522,520. Did you find your 2, Emma? Not yet. What about your 8? Did you get a 2 out of that? Did you remember that too? Okay. Lydia?
I just had a question. Why did you stop at 5 whenever you're on the numerator?
Just because it matched with the 5 on bottom.
Okay.
I didn't have to, but eventually we're going to be working with things like 52 factorial, and you're definitely not going to want to write down all of those numbers.
Would you normally stop whenever the numerator and denominator would start and then end?
I would normally stop as soon as the numerator matched something that's completely identical to the denominator, whatever the biggest thing in the denominator is. Yeah. So 2,522,520. And this would be the number of different ways that you could eat a package of 14 Starburst. Okay, that's crazy, right? It is kind of crazy. It is. Okay, so that's permutation of like objects, things that are indistinguishable. So that was method number 2. Method number 1 was fundamental principle of counting, for counting things. The second one is indistinguishable objects, like objects. The third one is distinguishable or unlike objects. So like if we were doing a calculation that involved you guys, right? You're all indistinguishable. I didn't say that right. You're all distinguishable. You're all different, right? None of you are alike. It's not like the 2 orange Starburst. It doesn't work like that. So one thing that you need to be careful of is that the part that's in red where it says order matters is what makes this different from my next method, okay? So these are unlike objects, things that you can distinguish between them. So this notation says that I'm choosing from in things. So imagine you have a basket of 50 objects or 100 objects, crayons, colored markers, marbles, whatever it is, okay? They're all different, though, in the basket that you're talking about. And what you're choosing is you're choosing out R of them, right? So maybe there are 16 crayons in the 16 crayon box, and you tell the child to choose 2, okay? How many different options could he have chosen if he chooses 2? Now, that's not the best situation to give you an example of because I want things where the order matters in order for it to be a permutation. The order needs to matter when you do this. So I'm going to do an example of one where that happens, but just for the moment before we get there, the way that this actually works is you have n factorial, so that would be my 16 crayons if that were really my example, 16 crayons on top, so 16 factorial. And on the bottom, we would subtract 16 minus that, what's left. So basically, it's the items that you didn't choose that's on bottom with a factorial. Okay? So here's an example where order matters. 30 contestants put their names in a hat for a raffle. First place wins $100. Second place wins $50. And third place wins $25. Okay? The order matters here because it's different if you get $100 or if you get $25, right? Yeah. So that's why this one, the order matters. It says, in how many different ways can the prizes be awarded? So we are choosing from 50 contestants, right? The order matters. So this is a permutation of unlike objects because we've got different people involved. And we're selecting 3 of the contestants. Oh, did I write it down wrong? I'm sorry. I saw my $50 is why I saw. Thank you. 30 contestants, we're choosing 3 of them. Thank you so much. Okay, so far so good? Okay, so what goes on top is my 30 contestants. And what goes on bottom is basically the number of contestants that don't win anything. It's the 30 minus 3. So you can write 30 minus 3 if you want. I'm just going to write down 27 and shortcut that step just a tiny bit. Okay, so Lydia, kind of back to your question on the earlier problem. Once we get to 30, I don't want to write out 30, right? I mean, 14 wouldn't have been bad when I got to 5, 5, 4, 3, 2, 1, not a big deal. But on this one, I really don't want to write this many numbers out. It becomes a big hassle. I mean, a really big hassle if I had to actually do that. So what I'm going to do instead is I'm going to write down the numbers until they match the biggest value that's factorized on the bottom. There's only one on the bottom, it's 37. So I'm going to write down 30, 29, 28, and then I have 27 factorial, which is exactly the 27 factorial on bottom. So at that point, the 27 factorials cancel because they match completely and totally. They don't just have something in common, they are completely and totally the same. And then your calculator only needs to multiply 3 numbers together, 30, 29, and 28. And if you do that, what do you get? 24,360 different ways. Now, just for fun, let's say that you knew that, right? We did that problem already. And then at part B asked you, well, what's the probability that you at least win something? Well, there's 3 different things you could win, right? So the number on top would be 3. And the number of different things that could actually really happen is the 24,360. That'd be your denominator. That's the real likelihood that you would win. Are you with me? Okay. Now, that's when order matters. My crayon example that I sort of inadvertently off the cuff threw out there a minute ago, order wouldn't matter. If I told the child there's 16 crayons and I want you to pick 2 of them, it doesn't matter if they pick red then green or if they pick green then red. They've got 2 crayons. It kind of doesn't make any difference, right? They're using those 2 crayons to color with, and then, crayon box goes to person number 2 or whatever it is we're doing. So on this one, it's called a combination. Combination order doesn't matter. So what you see is you see very much the same kind of formula you had before. You choose from n items, you're choosing r of them. The difference is that in the denominator, not only do you have the number of things you didn't choose with the factorial, you have the number of things you did choose with the factorial. So my crayon example, I'd have my 16 factorial on top, and then I'd have 14 factorial, the number of crayons I didn't choose, and then I'd have another 2 factorial on bottom, the number of things I did choose. Okay, so let's change my scenario with my raffle just slightly. And instead, I still have my 30 contestants, I still have 3 winners, but all 3 winners win the same thing. So now it doesn't matter if you're winner number 1 or winner number 3, your prize is the same. Your order doesn't matter. So this is a combination. I have 30 contestants, I have a combination choosing 3 of them. So I have 30 of them on top total, 27 that did not get chosen and 3 that did. So 27 factorial and 3 factorial. So this problem looks a bit more like my Starburst example because I have a couple of things on bottom instead of just 1. But the biggest one is still the same 27 that I had on the last one with the permutations problem. So I still will take 30 times 29 times 28 times 27 factorial. And I still have that 27 factorial on bottom. And then I'm going to write down 3 times 2 times 1. So once again, my 27 factorials, they cancel out. And if you wanted to, I mean, you could still multiply the top, multiply the bottom, and just let it divide on your calculator. Those numbers would not be insanely large. In fact, we know that because we already had this number over here, right? It wouldn't be crazy. But it's also true that that 3 and that 2 have to cancel with something on top. They have to. 3 times 2 is actually 6, and 6 evenly divides 30. So you could cancel it there if you wish. There's other places you could cancel it too. But we have a 5, a 29, and a 28 if I think about it that way. Or you can just multiply the top together, multiply the bottom 6, and do the division. So either way that you do that, you will end up still getting what value? 4,060. Notice it's much smaller. And that kind of makes sense because if the order doesn't matter, I should have fewer different options, right? Because it doesn't matter if I selected person A first or third. I don't have to count them as indistinguishable different things. They're not. They're the same now. So this is 4,060 ways. Now, a lot of our problems are going to have context that we're working with. In fact, most of them are. So you're going to have some kind of units you're writing down here. We're just looking for different ways. So that's why I'm sort of just writing down ways. Okay. I'd like to do 2 more examples and then we'll stop. I know that only leaves example 8 for next time, but I think that you will appreciate having a little bit more time working on group work on this section because the counting techniques can be kind of tricky. And if you get done with your group work and you move into your homework, even better, okay? So I've got 2 more examples for you, and then we'll be done for today. All right, if we have all the phone numbers for a large business, and they start out 405767, and then we have the 4-digit extension at the end, or the 4-digit number at the end, how many different phone numbers are possible? All right, so as we move through examples 6 and 7, at least for today, and through all your examples, you have to decide. I've got 4 different ways of doing counting, right? How is this one going to work out? Is it fundamental principle of counting? Is it permutation of unlike objects? Is it permutation of like objects, or is it a combination? I have 4 options. So I have this problem. What kind of problem does this sort of feel like maybe to you? What do you think, Izzy?
Permutation of unlike objects.
Permutation of unlike objects is definitely one of the options. There's 2 ways that you can think about this one. So let's go with the one you think. So if I did permutation of unlike objects, it's a little bit tricky. So that would mean that there's 4 numbers I'm choosing at the end, right? So I'm choosing 4 numbers. And I have how many numbers to choose from? More 10. I have 10 digits because I have 0 through 9. The problem with permutation of unlike objects is that, like, think about my winners of my raffle. The winners of the raffle, once they win, they can't win again, right? But does that work for a phone number? No. Once you actually use the digits, you could use the digit again. So it feels like it should be that, but because I have the ability to repeat my numbers, it's not permutation of unlike objects. What else might it be? So this is a pretty good one to use a fundamental principle of counting on. I have 4 different numbers at the end, and because I have the ability to choose something over again, I have 10 choices for my first digit, and I have 10 choices for my second digit, 10 for the third, and 10 for the fourth. So there are actually this many different phone number options available. What is 10 times 10 times 10 times 10? It is 10,000. There are 10,000 numbers. That's a really big number set for this company, right? Yeah, I mean, 10,000 employees would be a huge company. So we could have 10,000 employees before we ran out of numbers if this was our scenario. Now, some of the times they're going to give you some examples where they limit, like Izzy, the one you just talked about, where they'll say without the numbers repeating, and then you could use that one and it would work. Or you could still do it as a fundamental principle of counting and do it that way. Number 7 is one where we actually have 2 choices that actually legit work. A worship team practices 8 songs on a Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? So this phrase where it says in how many ways is kind of a red flag phrase. This phrase actually tells you that the order matters because it says in how many ways, right? So the ways are different. So if I sing, how great there are first, or I sing it third, it would be a different ordering. Also, if you have been in any worship services before, you probably recognize that there is sort of an ebb and a flow to the way music is chosen. It's not willy-nilly, right? They don't just randomly put the songs in there. You don't go from a fast song to a slow song and back to a fast song. Like that's not the way things typically go. The order matters in the flow of the worship service. So it makes sense that it would also be that order matters. So this one actually could be done with the permutation of unlike objects. I'll show you one more way it could be done, but this would be 8 worship songs and we're going to choose 5 of them. So I would have 8 factorial over, and remember the denominator is 8 minus 5, it's the songs that aren't chosen, so 3 factorial. So 8 times 7 times 6 times 5 times 4 times, and I might as well stop at 3 factorial so that it will cancel with my 3 factorial on bottom. Even though the numbers are small, we'll shortcut our system just a little bit. And if I multiply that out, 87654, there are 6,720 different ways this could happen. Now, I also could do this problem with the fundamental principle of counting. I'm choosing 5 songs. How many songs do I have to pick from initially? 8. After that, how many do I have? 7. We're assuming we're not repeating songs. I think that makes sense in our context. And then I would have 6 and 5 and 4. Of course, that's the same list of numbers I did before. And it will result in the same 6,720 different ways that I could organize the songs in a worship set. All right. We will pick back up here next time. Please, please, please make sure that you have turned in your redos by next time, especially since there's no homework tonight. They are due next time, and I'll see you guys on Wednesday.